Okay, so in this video, I'm going to continue to cover section 3.1, the Lagrange Interpolating Polynomial. Okay, so last video, we I introduced how to write the MATLAB code of the interpolating polynomial, right? So as you can see here in the screen, yeah, I made the code, the MATLAB code, through the Octave Online. So Octave Online is pretty much the same as MATLAB, but it's free, open license. So anyone can use this Octave Online, the program. Let me see. So as you can see that yeah. So right there, I wrote the code, and then now some of you maybe some of you don't know how to run the code. All right, so when you run this code, please keep in mind the structure of the input D and W. Okay, so D, what's D? Right, as you can see that D is the what the n plus 1 by 2 matrix, and then first column is nodes. Second column is the list of the function values at each node. Okay, and then W is the x value right there. Okay, x value. So the W is also a column vector. Okay, so let's see. Okay, so now we're gonna to run this one, first one. Yeah, let me solve the let me approximate the function 1 over x using 3 nodes in the example in textbook. Give me a second. So that is in the textbook. Give me a second. Yeah, right there. So as you can see that the example 1, this is an example in textbook, right? So the 3 nodes are given 2, 2.5, 4, and then we assume that we know function value at 3 nodes, x0, x1, x2, okay? And then f of x is defined as 1 over x, but we assume that we don't know f of x, okay? So then I want to construct the approximate polynomial using the second order. Since there are 3 nodes, so when you construct the Lagrange polynomial, we're going to get the degree 2 Lagrange polynomial, right? So we are going to deconstruct the approximate polynomial to f of x using degree 2 Lagrange polynomials, interpolating polynomial, okay? And then we want to see that the code return the 0.325 at x is 3. Okay, so give me a second. Okay, so now here, first one, D is equal to 2 and 2.5 and 4. That's the these are nodes, right? Okay, so but when you the write the 2, 2.5, and 4, then we'll get the row vector, not column vector. Okay, so eventually we have to transpose the matrix D. Okay, I'll show you. Okay, and then the column must be 1/2, and then 1/2.5, and then 1/4. Okay, these are function values at nodes 2, 2.5, 4. Okay, so and then we'll see it here. As you can see that, look at this, 2, 2.5, and 4, and then 0.5, 0.4, 0.2. So we have to get the 2, 2.5, and 4 in a column, not in a row. So we transpose. How can transpose? We put the prime. Okay. Then you see that we're gonna get we transpose D. Then we're gonna get 2, 2.54. We're gonna get the nodes in a column, and then second column must be function values. All right, so next one, W. Then W is, yeah, just we want to approximate the f of 3, right? We want to approximate f of 3, but let me add 1, 2, 3, 4, 5, okay? Right there. So now then W is 1, 2, 3, 4, 5. So, because I want to test this code, I want to test that code if this code is working at when the input W is not just a single real number, but a column vector. Okay. So, by the way, W must be column vector, so I'm gonna transpose W too. Okay. Now we put P is equal to, we plug in D and W into the function. I mean, we're gonna run the function using the W and D. Okay, D comma W. All right. So now you see that the first number is what? Approximation to f of 1. The second number is what? Approximation to f of 2. This is approximation to f of 3. So as you can see that 0.325, this is exactly the same number decimal as the answer in the example textbook. Okay, so it means that this code is working. But I want to visualize our result earned by that code. Okay, program. So so to do that, there are several ways to visualize. I mean, plot the graph. Okay, and then I want to plot error too. I want to calculate error too. So how can I do that? So let me see, P. First one, we just generate the mesh points. Okay, we can say mesh point or lens. Mesh point. Okay, mesh point, then 0 through the maybe 5, and then 100. Okay, that will generate the 100, the mesh point from 0 to 5. Okay, right there. So now then we plot the x, and then 1/x. So here, the reason that I put you see that here dot right there, because x is not a single number. Since x is the vector, right? I mean, x is the matrix. Okay, I'm showing you. What is x? And you can see that x is the row vector. So the size of x is what? 1 by 100 matrix. This is a row vector, right? So the then when we then x is the first number in the plot, the command. The first input must be x value. Second input must be y value. that we evaluate each entry in a row vector X by 1 over X, and 1 over, f of X, which is 1 over X. So we divide each entry by its value, the entry. Okay, so then we use this one dot. Okay, so we're gonna get this one, right? And I want to figure. I want to just add the compare. Yeah, this is the exact the graph of the exact solution 1 over f of x 1 over x. I want to compare this one with our approximate polynomial. Okay, then we just hold on and then plot x, comma, and then what in TRPOL, this one, d comma x prime, because x is row vector. When you enter the x into the function interpol, we have to transpose. Okay, so now, so as you can see that you see that here the red the graph is the approximate graph of approximate solution, approximate polynomial, and then blue curve is the graph of f of x. So since we use only degree 2 Lagrange polynomial, so as you can see that as x approaches 0, the error is exponentially increase, right? Okay, right. But and then also there we use only 3 nodes, 2, 2.5, and 4. Then we can expect you can expect that the our approximate polynomial is more accurate around the 2 to 4 than other, the rest of the interval. Okay, so but let me increase the number of degree. Okay, so d is equal to 0.5 and 1. Let me say node is equal to 0.5, 1, 1.5, and 2, and 2.5, and 3, and 3.5, and 4, and 4.5, and 5. Okay, so prime. Okay, and then d is equal to node. Let's see. And then node 1 over. So we got this. So if you use a comma, that means the not the go move to next row, but next column. Okay. So so second column is the function value at each node. So how many nodes we use? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes. We use 10 nodes. It means that then we can the code will generate the 9th degree Lagrange polynomial, right? So anyway, so we plot, see dx prime. Yeah, we run this one. Then you see the is I think it's orange. So orange is this color core is the more close to the closer to the graph of the exact solution, right? Okay. So now, so yeah, we'll see the and then I want to also, if you want to figure out the error, then we need to modify the program, the code. So let me do, let me modify the code, okay, next class, okay, because I need to cover the theorems in 3.1, okay. So, because since the theorem is about the truncation error, so once I cover the theorems, okay, and then we understand the truncation, how what does the truncation error look like, okay, allowing interpolating approximate polynomial of interpolating using interpolating polynomial, and then we're gonna write code to calculate error, and then we're gonna compare the theoretical error and the numerical error. Okay, so let me see here. Give me a second. Not this one. So let me let's see here. Share. Sorry, I need to find out my lecture note. Give me a second. Okay. Interesting. Okay, give me a second. Let me see. Sorry, so in my laptop, yeah, so many windows open now, so it's hard to find out which window is the lecture note what I'm looking for. So maybe this one. Not this one. I'm sorry. Okay, then. Okay. Oh yeah, this one. Yeah, I found it. Okay, so all right. So here, so the error term for the Lagrange polynomial. So that's what we're gonna do. All right. So see theorem right there, 3.3. They suppose that x0 through xn are definitely these are those. Okay. There are n plus one distinct nodes are given. We assume that, and then the f of x, the function f is the n plus one. I mean, up to n plus one derivative. I mean, continuous function up to n plus one derivative. Okay, then there you could use cosine of x. Okay, generally unknown. Yeah, and then such that f of x is equal to p of x plus this one. Okay, so actually this is the remainder term, and then it's called the truncation error. Okay, the p of x is an interpolating polynomial, so it means that the difference between the f of x and then, I mean, approximate polynomial using Lagrange polynomial, that's p of x. Difference between f of x and p of x is this. So this is truncation error. Okay, this is truncation error. So then, okay, so then you may wonder that, okay, so see, in a theorem says that, okay, there is a cosine of x, but generally unknown, right? Then how can you figure out specifically, I mean, the value of that truncation error. Okay, so x0, I mean x minus x0, x minus x1 through x minus xn. Okay, it's not a big deal to figure out, to calculate this one, because x0 through xn are given, right? Because these are nodes. N plus 1, yeah, not a big deal to figure out the numerator. The denominator, since function f is the cn plus 1, so there exists n plus 1th the derivative of f. Okay, but since we don't know cos of x, so then we need to find out the upper bound of function f. Okay, so definitely this guy gonna be, I mean, that truncation error must be less than or equals bounded by m, okay, over, and then m plus 1 factorial, because m is what the give me a second, I think the yeah, I was okay, sorry, it's just the color of the pen is really light, so okay, so bright, so m plus 1 factorial, okay, and then times x minus x 0 times x minus x1. So here m is the upper bound of the m plus 1th derivative of f. Okay, so then we can this can be used as the the error estimate. All right, so keep in mind this, and then the second thing that I want to tell you is do not confuse with the what? Do not confuse with the truncation error in a Taylor polynomial. Okay, so yeah, this is exactly same as the the fraction in a truncation error of Taylor polynomial, right? But x minus x0 times x minus x, and this is the not the same form in the truncation error of Taylor polynomial. Okay, don't be confused. So let me I'm gonna explain the proof of this theorem, okay, briefly. So I know just proof of theorem is always tough, so you may don't it's hard, it's probably it's hard to understand this. Okay, so but let me cover this one. Okay, now then the first one, keep in mind this, what's the goal? Goal is to show that the existence of psi of x. Okay, keep in mind this. All right, so keep in mind this. So first one, if x is xk, what does that mean? So we can think about two cases. What? Here, two cases. X is, what if x is one of the nodes? And then what if x is not one of those? Okay, if x is one of nodes, okay, xk is a node, okay? Kth node, right? Then since f of xk equals p of xk, actually that's the nice one of the, I mean, that's the interpolating property, right? Interpolating property. Okay, so that's why then f of xk equals p of xk for any psi of xk. You see that for any psi, f of xk must be equal to p of xk. Right? So it's, and then also the x, we're gonna get the xk minus xk in a truncation term. So truncation term gonna be 0. So it's trivial. Trivial means that what? There for any psi, f of x equals p of x plus 0. So we just we complete to prove the existence of the psi. What's the psi? Any real number in the interval a through b. Okay. So now next one. So the second case is the yeah, actually the problem, the things. So second case, what if x is not equal to xk? All right. Then first we define function g of t, which is this. Okay, f of t minus p of t minus f of x minus p of x times this one. But you see that here, this one? This is the actually what? From the definition of Lagrange interpolating polynomial, right? Okay, it's pretty much, I mean, not exactly same, but it looks like similar, right? Okay, similar to the definition of Lagrange polynomial. Anyway, we define g of t as like this. Okay, why we have to define g of t like this? We'll see. We'll see. Okay. So then you know, short expression of this fraction is pi t minus xi over x minus xi, right? And the f of yeah, and then also we by the assumption that f is a c f function f belong to Cn plus 1, okay, and then p is c infinity. Oh, wait a second, f belong to Cn plus 1. That makes sense because of that from the assumption. But why p belong to C infinity? Because p is what? Polynomial, okay? So polynomial is a what? Belong to C infinity. Any polynomial function belong to C infinity. Keep in mind this. So that makes sense. All right. So now look, go back to the definition of g of t. G of t is f of t minus p of t minus f of x minus p of x, and then this one right here. Okay. So by the way, what is this? This is also polynomial. The pi t minus xi over x minus xi. Keep in mind this. What's the unknown variable? T. T is unknown variable. Okay. So f of x minus p of x is now x is we assume that x is given as a real specific real number. Okay, but not one of those. So f of x minus f of x is real number, and this is polynomial, right? And then f of t is belong to C infinity, Cn plus 1, p of t belong to C infinity, okay? Then g belong to C n plus 1. Does it make sense? Because that polynomial belong to C infinity. This one belong to C infinity. This one belong to C n plus 1. Okay, then g belong to C n plus 1, right? Okay, so for t is equal to tk now, t equals x sub k. Okay, t means t. So for when t is node t equals node xk, then g of xk gonna be f of xk minus p of xk minus this. But you see, since this polynomial gonna be 0 when t equals x sub k, and then since p of xk is equal to f of xk, so f of xk minus p of xk is 0. So g of xk equals 0. Okay. So now, next one. Give me a second. Next page. So next one. Oh, yep. Okay. Next one. Let me see. All right. So far we have shown that g of xk equals 0. Okay. All right. And then now we're gonna now we're gonna show that g of x equals 0. Okay. You see. So g of x, therefore g of x equals 0. Why? Because your f of x minus the p of x minus f of x minus p of x times this fraction. We'll see that here. Okay. So the substituting the x into t, we're gonna get x minus xi over x minus xi, which is 1. So we multiply 1 as I goes 0 through n. So what? 1 times 1 times 1 is just 1, right? So f of x minus p of x minus f of x minus p of x, 0. Okay? So g of x equals 0. All right. So now then, so far what we figured out is this. G belong to Cn plus 1. And then g of t equals 0 at t is x, x is 0, x1 through xn. Okay? All right. So then we're going to use generalized rule theorem. What does it, by the way, what does that mean? G of t equals 0 at t is x, x0, x0, x1 through x sub n. It means that these are zeros, right? X sub 0, x sub 1 through xn, these are zeros of the polynomial function g. Okay, and then g is Cn plus 1. By the generalized rule theorem, there exists psi such that g to the n plus 1 derivative equals 0 at psi. Okay, so if you yeah, just, if you just don't know what general rules theorem, then please go back to the 1.1. Okay, so let me keep continuing to look at this. Okay, so g, so now then g n plus 1 prime psi, this is equal to, so we figure that now what are you going to do? We're going to figure out n plus 1th derivative of g. Okay, since we know the g, right? We define g, right? So then f the f of n plus 1 derivative of f minus n plus 1 derivative of p. What? By the way, so this is 0, right? Why? Because p is what? Approximate polynomial using nth degree Lagrange polynomial. Okay? So it means that degree of p is what? N. Okay? For any nth degree polynomial, if you take the derivative n times, we're gonna get 0. Okay? Think about the just linear, degree 1 polynomial. Then if you just take a derivative twice, we're gonna get 0, right? If you think about just the quadratic polynomial, degree 2 polynomial, if you just take a derivative 3 times, you'll get 0. Likewise, since p is a degree n polynomial, if you take a derivative n plus 1 times, that's going to be 0. Okay? So p, n plus 1 derivative p going to be 0. And then look at this. We take a derivative, this guy, with respect to t n plus 1 times. Okay? All right? So let's see now. All right, so, okay, just give me a second. All right. All right, so now the thing is this. We need to figure out this guy. Yeah, so eventually we plug in a psi into t, but so derivative of this guy is what? That is equal to, first one, think about the first derivative. I think I need to use the my sketch paper, so give me a second. So, okay, say, all right. Okay, so now right here, we want to figure out d n plus 1. You see this, right? Over d and then t to the n plus 1. Okay, and then pi I goes 0 to the n, and then t minus xi. So if you yeah, this proof will help us to find out derivative of Lagrange interpolating polynomial. Okay, eventually we have to write the code to calculating the derivative of Lagrange interpolating polynomial. So this will help to understand the how to design the algorithm to find out the derivative of Lagrange interpolating polynomial. Okay, so this one, and then or and t is equal to psi. So that is equal to, this is equal to right here. So this is equal to, now let me see, 0. Yeah, the first one, let me see. Okay, right here. So think about just a derivative, just first derivative of this guy. Pi, I goes to 0 and n, and then t minus xi over x minus xi. Okay, now, so before figuring out this one, okay, we don't know yet. Yeah, we'll just think about just first derivative. Okay, then this is equal to what? Okay, we don't have to take care of the bottom one, the denominator. Denominator is just a number, right? Okay, so the thing is the numerator. But numerator is a product of the binomial, right? So how can you find out derivative of the product of binomial? We have to use, I mean, there is other way, but usually we have to apply the product rule of derivative, right? So it means that t minus x0 prime, right? And then t minus x1 through the t minus xn plus, here's a plus, and then t minus minus x0, and then t minus x1 prime times t minus x2 through the t minus xn, then plus, now you see that here, t minus x0, and then t minus x1, and then t minus x2 prime times the t minus x3 through the t minus xn. Keep going until what? We got the t minus x0 times, and then t minus xn prime. That's going to be numerator. That's going to be numerator divided by denominator, right? X minus x0, excuse me, and then x minus x1 through the x minus xn. I see. Okay, see. All right. All right. So now, let me see. One. Okay. So now this is equal to yes. Okay. Yeah, this is equal to then 1 over give me a second. Yeah, this is equal to 1 over. So let me take out the that numerators. Okay. So this is a pi. I goes to 0 through the n, and then x minus xi right here, and then times the what? Derivative. So I mean, so this is times, and then back to here. Think about this. What's the first? What's the derivative t minus x0? 1, right? This is equal to 1. Okay. Right. And then so t minus x2 is also 1, right? And t minus xn also 1. Okay. So now then, yeah, this is going to be, yeah, t minus x1 minus x1 through the t minus xn, right? And then plus t minus x 0, the t minus x2 through the t minus xn, isn't it? And plus through the t minus x0 through the t minus xn minus 1. Oh, like this. Okay, you see. So first derivative, we got this. And the first derivative, so we got the m plus 1 terms of product of the binomial. Each product of the binomial is a degree. Now degree is not n degree n plus degree n, but degree n plus 1, but degree n now. You see that? This is degree n, nth degree, nth degree. And then plus through here, this is nth degree. You see? Okay, nth degree to nth degree. So now, then guess what? So if you take a second derivative, taking second derivative, then this is equal to 1 over pi, I goes 0 to n, and then x minus xi, and then d dt, and this one, right? Okay. Right. So now then what? Then we're gonna get the so for each one, what we're gonna get the how many terms we have? So the n plus 1, right? So there are n plus 1 terms, but we're gonna get the m. Give me a second. Let's see. This will be derivative. This guy will gonna be n times n plus 1 terms, right? Is it n times n plus 1 terms? Okay, and then also degree of each terms. Degree of each term is going to be degree of the each product of the binomial going to be n minus 1. So can you see that the degree of each term is decreasing from n plus 1 to from n plus 1 to n minus 1 through the 0, because eventually we're going to take a derivative n plus 1 times. So we know that each term will become 1 when you take a derivative n plus 1 times. Is it? Okay. Why are we going to go 1? Because you see that here, this one is nothing but what? T to the nth power, right? Plus something. So what I mean is this. So the d dt is equal to 1 over pi, I goes 0 to the n, and the x minus xi. This is equal to what we got? T minus d dt. Oops, not this one. D dt. Sorry. Oh, sorry. Give me a second. Let me do it again. D dt. Okay, d dt, and then pi, I goes 0 to the n, and then t minus xi over x minus xi. This is equal to, what is this? 1 over pi, I goes to 0 and n, and then x minus xi times, and then what we got is a t minus x1, and then through the t minus xn plus t minus x0, and then t minus x2 through the t minus xn, right? Okay, and then plus through the t minus x0 through the t minus xn minus 1. Okay, so now then, this is equal to 1 over pi I goes 0 n, and then x minus xi times, what's the first term? We can say that this is a t to the nth, nth power plus something, plus, and then t to the nth power plus something, right? Plus through the t plus t to the nth power plus all the terms. We can say that. Right? So this is equal to 1 over pi I goes 0 and n, and then x minus xi times, how many terms right there? How many terms? N plus 1, right? N plus 1. So you got n plus 1 times t to the nth power plus something. Right? And then we take a derivative one more times, the second power here, and then pi I goes to 0 and n, and then t minus xi over x minus xi. That is equal to the derivative d dt, and then what? 1 over pi I goes to 0 and n, and the x minus xi times, yeah, let me do again. Okay, n plus 1 t to the nth power plus, you see? Then this is equal to what? 1 over pi I goes to 0 and n, x minus, this is just a constant, right? So we just leave it, okay? Times the derivative of this guy is what? n plus 1 times n times t to the n minus 1 something. Okay, so keep going. Then eventually we're going to get n plus 1 factorial. When you take a derivative n plus 1 times, we're going to get the n plus 1 factorial here. That term becomes n plus 1 factorial. So finally, what we got, so now what we're going to do, what we're doing is to what? We want to figure out the n plus 1 derivative of g at t equals cosine, right? That was f of n plus 1, okay, n plus 1 of cosine, and then minus p to the n plus 1 derivative of cosine. It turns out to be 0, right? Because p is a degree n Lagrange degree n polynomial, right? And then minus f of x minus g of x, okay, times right there. That was what? n plus 1's derivative with respect t, and then pi I goes 0 to the n, and then t minus xi over x minus xi, right? And then t is equal to cosine, right? So then this is equal to what? F of, now we can say f of the n plus 1's derivative at cosine minus f of x minus p of x, and then it turns out to be what? This is equal to n plus 1 factorial divided by what? Pi I goes 0 through the n, and then x minus xi. Now we by the generalized rule theorem, this is equal to 0. Okay, what's a generalized rule theorem? General rule theorem is this: if the what? Let me see, 0 and okay. If function, so think about this: function is 1, 2, 3, 1, 2, 3, 4, 5. Okay, so general rule theorem is this: if the function f of x, this is a graph of f. Okay, f of x. Okay, the f belong to the what, here 1, 2, 3, 4, 5. Okay, so the c to the fifth power, c5 space. Okay, let's say here's a and b. Okay, so this is a comma b right there. Then let's say this is x1, x2, x3, x4, and x5. So function f has 1, 2, 3, 4, 5, 5 root. Let's say 5 is root. Okay, function f has 5 root, and if f is a c5, belong to c5, then the fourth derivative of f at cosine equal 0, there exists cosine. Okay, belong to a comma b, such that fourth derivative cosine. Okay, all right, human. So that's the generalized rule theorems. So g n plus function g, t minus g was what? So g t was 0 at what? T is equal to dx, right? And then x is 0 through the xn. So how many roots how many roots g has? N plus 2, right? So applying the generalized rule theorems, then there exists cosine such that n plus 1's derivative of g equals 0. Okay, so so far we got this. 0 is equal to this one. 0 is equal to f of n plus 1 derivative of f minus this. And then we solve this one for f. Okay, so 0 equals f of n plus 1, then cosine minus f of x minus p of x, and then n plus 1 factorial over pi I equals 0 to the n and the x minus xi. And then we solve this equation for f. Okay, then what? The next one, let me use now script, like my lecture note. Okay, so okay. Oh, oh no. All right, so now let's see. Okay, I'm sure that you can see my lecture note. All right, so give me a second, just a second, next bit. Yeah, okay, so G0, not this one. Oh, I'm sorry, it's not this one, sorry. Yep, not this one, give me a second. Oh. All right, so now I found it, okay. Yep, okay. So as you can see, oh, let me zoom in. Okay, so now, so finally, yeah, we got this. F of x is equal to P of x plus this one. Let's see. So this is the what? Exactly same the formula shown in the theorem 3.3, right? So proof is done. Okay. All right. So now let's see. Now we're going to compare the Lagrange polynomial with Taylor polynomial. Okay, so nth Taylor polynomial is about x0. We concentrate all the known information at x0 and has the error term of the form this. Okay, so what that means, the big difference between the Lagrange polynomial and the Taylor polynomial is Lagrange polynomial is use the not just the information the at x0, but information all of nodes x0 through xn. Okay, you see here the Lagrange polynomial of degree n use information at the distinct numbers. Okay, so in place of x minus x0 n plus 1, which is the what? Which is the product of binomial terms in Taylor polynomial, right? This, right? The Lagrange polynomial replace this one by x minus x0 through the x minus xn. Okay. All right. So this is a big difference. So what does that mean? Normally you see that in a Taylor the accuracy Taylor polynomial is getting worse and worse as x is away from the center point x0, right? But Lagrange polynomial is not. Okay, Lagrange polynomial, since Lagrange polynomial use the information of all nodes x0 to xn, so Lagrange polynomial is doesn't have that kind of the drawback. Now then, see, next one is okay. Example 2. All right, let's see example 2. So f of x is equal to e to the x given that, and the h is the step size, the difference between adjacent x value. Then what should the h be for linear interpolation to give an absolute error of at most 10 to negative 6? All right, so we have to decide the h, right? H is the step size, the difference between adjacent x value. So first one, let x0, okay. Let x0 through the xj, and then yeah, there are many nodes. Let's say that there are nodes x0 through maybe xn. Okay. So now let me show next page. Oh. All right. So now then. Oh, you see that? Okay. Now we're gonna decalculate the difference between f of x minus p of x. Okay. Why we have to calculate this one? Because we want to find out the what h, so that we're gonna have the error within 10 to negative 6, right? And we have to use error estimate and theorem 3.3. Okay, so error between absolute error between f of x and minus p of x is this. Let's see, okay, right. Then the x minus xj and the x minus xj plus 1. So using the triangular inequality, oh no, not triangular. I'm sorry, not triangular inequality. I mean just the what absolute value of the product of term is equal to the product of the absolute value of each term, right? So we got this, and then since step size a is h is step size, right? It means that what xj is equal to j times h, and then xj plus 1 is equal to j plus 1 times h. That's the meaning of step size. Okay, so now then we're gonna plug in j times h into xj, okay, and then j plus 1 times h, that plug into xj plus 1. Okay, so we're gonna get this right there. Now then, Also the what second derivative f, what is f? F is defined by e to the x, right? So the second derivative f is still e to the x, and then so f second derivative f at cosine is e to the cosine. Okay. Then e to the cosine is bounded by what? Maximum of e to the cosine, and the cosine is between 0 and 1, right? Okay. So what's the maximum of e to the cosine? And the cosine is between 0 and 1. E, right? A natural number e. So max f of x minus p of x is bounded by 1/2 times maximum of the second derivative f, which is 1. Sorry, e, natural number e. And then times the maximum of this one, right? So finally we got this 1/2 times e and the maximum of this. Keep in mind this x is between what? Xj and xj plus 1. Okay? X is between xj and xj plus 1. Now then, let me see. I mean, okay, so you may wonder that, oh, why x is between xj and xj plus 1? Because look at this. This is the quadratic polynomial, right, of x. Okay? And then this quadratic polynomial, what? Let me see. Okay, quadratic polynomial x, and then this quadratic polynomial has two x-intercept, xj and xj plus 1. So graph of the this guy must be like this. Okay, maybe this is xj. Okay, then maybe this here is xj plus 1. J plus 1, right? Okay. Then we know that the minimum value of this quadratic polynomial is what? Right there, vertex point, right? And then you see that here, there's absolute value. Taking absolute value of this quadratic polynomial, then the minimum value, which is a vertex point, going to be maximum value, right? So the x is between xj and xj plus 1. Okay, you can hear this. So now let's say g of x, define g as x minus xa in here, xj plus 1. Yeah, so we're gonna find out. Yeah, so once for convenience, we let g as like this, and we're gonna find a vertex point, this one. Okay, so now let me see. Okay, oh, it's done. All right, so then so we know that the vertex point gonna be what? Let me see. So it's so what? Negative b over 2a, right? So once we figure out a, b, c, I mean, expressing g, rewrite g as the standard form of quadratic polynomial, okay, to figure out a, b, and c, right? And then what? X coordinate of vertex point is going to be negative b over 2a. So applying this formula, which is in closed algebra stuff, right? Then we easily figure out that the y coordinate of vertex point is going to be h squared over 4. Okay, so now we see. Let's see. Okay, now next page. Oh. All right, so now the error in the linear interpolation is bounded by 1/2 times e times h squared over 4, which is e h squared over 4. Okay. So now then we want to determine h, so the error is within 10 to negative 6. So we solve the that inequality. Okay. Now we see that here, that inequality. Solving that inequality, we're gonna get this. All right. So, okay. And then what? The n must be what? 1 minus 0, because 1. So we wanna we wanna approximate f of x in over 0 to 1, right? So that's why top is 1 minus 0, and the bottom one is 8. So we just got 8, right? Okay. So now then n must be integer. So we choose h as a 0.001. That what is this? 1.72 times 10 to negative 3. This is a point, right? Okay. 0, 0. I mean 0.00172, right? So 0.001 must be less than 1.72 times 10 to negative 3. Okay. All right. And then so we don't have time. So please please implement this example to the code. Okay, so see, you're gonna get the same result in the table in the textbook. All right. So okay. So the last one is this note. Particular difficulty with the line of interpolation is that since the error term is difficult to apply, the degree of the polynomial needed for the desired accuracy is generally not known until computations are determined. Yeah, so you understand what I'm saying? What that says? The particular difficulty with the line interpolation is that since the error term is difficult to apply, why error term is difficult to apply? Because we have to figure out n plus 1's derivative of the f, exact solution, right? Okay, so, and then also the, not like a Taylor polynomial, the product, I mean, we have to calculate x minus x0 times x minus x1 through x minus xn, right? So this is also the increase the amount of computation, I mean, computational cost. Okay, so, all right, so let me stop here. Okay, so next time I'm gonna cover the 3.2, all right? And then next video, I'm gonna cover the 3.2, and then maybe I'll review the 3.1 briefly, okay? So let me stop here. All right, so please be safe, okay? And then see you next time.